This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known. Hello, welcome to the Math Map Book Club, where Kirsty Gilpin and I each week discuss lessons from the Math Map, a math curriculum for students enrolled in classical conversations communities. And this is summertime, so we're doing something a little bit different. Each week we're going over a couple of games that are included in the Math Map curriculum. And so we've had some special guests as well as our usual folks. So Kirsty, what do we have today?
So today, there we go. So today we are looking at Battleship and then missing angles. Babs and Jill are going to be leading us today. And let me just make sure I've got my screen right here so that I can advance our slides. So just as a reminder that we are doing 2 booklets per week. We're looking at the games and the activities, and we may be a little bit ahead of you in your summer planning because that's just as a reminder, that's the goal of this book club has been to equip parents to work through the math map at home. And so that's why we started back in July, and we've tried to stay ahead of everybody so that for those of you who are participating live or watching the recordings of the book club, we're hoping that this is going to help you to feel equipped as you work through the math map at home with your students. And so in the same way of wanting to be a little bit ahead of where you would be, we're looking at these games and activities as ways that you could keep the math conversation and the math excitement going throughout the summer and not lose steam, even if you're not actually doing lesson pages as you might traditionally during your academic year, the CC academic year. So it was fun. I was talking with some people the other day, and they were all commenting that this was the very first time in years that they were not behind in math and that they hadn't finished their CC year, but still had 100 pages left in their Saxon textbook. And so I think one of the things that I really appreciate Lee doing as she designed this curriculum was really tailoring that to the challenge year so that you can have that sense of we've finished, we've wrapped up our academic year and we've stayed on track and nobody has to feel behind anymore. But we want to keep that conversation going. And so these games and activities are a great way to do that. So we are going to turn this over now to Miss Babs, and she is going to work through Battleship with us.
Okay, so this game is pretty easy. I know we're not really supposed to say easy, but we're not talking about math here. We're talking about playing the game. And I think most of us have probably played Battleship at some point. And so we probably won't spend a whole lot of time on the specific instructions, but I have some ways that we can tailor it depending on the ages or levels of your student. So in this way, if we want to use this particular backdrop and fold it down the middle so that one side gives you, one opponent's ships and their opponents, and the other side, is another player. And so the way Battleship is played, these instructions are just like the ones in the regular Battleship game. I actually got mine out. I was surprised that I actually still had one. It's probably because I haven't cleaned out the game closet in many, many, many years, and we still have games from when they were in preschool, but probably need to do that. But anyway, getting out the Battleship game just kind of helped, see that these instructions are exactly the same. So every player will choose some squares that correspond to a particular ship. So they have like a battleship, a destroyer, an aircraft carrier, and we can mark those on our grid. And then our opponent will do the same thing. And then players take turns naming points. And so what I was talking to Kirsty on Monday about, so what are we actually practicing here? And we're really practicing plotting points. And I thought that that was something that students just knew how to do until we started the math map. And I think it was Christmas time. This was in the pilot, we tried to get our kids to make Christmas tree, like the Christmas tree outline. And I realized how many kids don't know how to plot points. And so it took us a good amount of time to just make sure everybody understood, right, how to call out the left side or the top or the right side or the top, depending on what kind of grid they were using. So it really does help us kind of practice those points. So as let's say I'll guess D3, and if my opponent had a ship there, he would tell me that that was a hit. But if there was no ship there, if he hadn't colored in one of those areas, then it was a miss. And so we can go back and forth doing that until all of our ships have been sunk. You could put a time limit on it, because I know when we've played Battleship in the past, it could go on forever and ever and ever. So you could just have a time limit of, we're going to play for 15 minutes, and whoever, mark or hits the most, most spots wins, and that kind of thing. So that's the basic instructions for the game. And like I said, they're almost identical to the ones that we play in the regular Battleship. So if we'll go to the next slide, these are some ways that we can kind of tailor the curriculum. So instead of using the actual Battleship board, we could use graph paper, and we could create our own Battleship board with different kinds of numbers. And so we could use integers or decimals or fractions or complex numbers, whatever your student is working through, maybe something you want to review with your students. So this one that I found had the imaginary numbers, and it also had integers, but you could choose whatever you wanted depending on what you wanted them to review. So this could be for our younger students, it's probably okay, to just do the natural numbers, or maybe the natural numbers and integers, right? But for some of our older students who are being introduced to those imaginary numbers, I think this kind of shows them that they're not scary, right? Because we're just adding an I to an existing set of numbers. So this is a good way to kind of see that visual. And so just to kind of change it up a bit, we could make our own grid, and then we could put whatever numbers we want. So that's one way that we can kind of tailor to our student. And then let's look at the next one. So the next one, I feel like this is a really good way to practice multiplication, is using the multiplication table from a couple weeks ago. We were using the multiplication table from week 5. And they can practice their times tables by saying, okay, instead of, a grid of, A1 or D4, you could say 4 times 8. And if their mark was on that 32, then that could be a hit, right? And so we're kind of talking through this the other day. You'd probably have to decide in your rules. Are you going to allow 8 times 4? Because 8 times 4 is still 32, but it's way down there at the bottom. And so if you still want to go with this idea of location, then I would probably say, no, we wouldn't use that rule. Like, I'm still practicing my multiplication, but you're not going to get a hit because it's not in the spot where I actually put my mark. So you can kind of decide, how you want to tailor that in that way. So this is a great way to practice our multiplication tables, because we hear about calculation all the time. And I was talking to somebody this week about the difference between flashcards and maybe playing games. And other people might have different opinions. My opinion was, if I'm drilling a flashcard, that's pretty fast, right? I can do that quickly. But if I'm playing a game, it gives me a little more time to think through an answer. And so I feel like, maybe not, maybe kids, are quicker when they play games too. But I feel like when I'm playing a game and there's other rules involved, I have to think about the rules and the calculation. And so there's more things I'm thinking through than just I'm drilling a flashcard. So this is just another way we could practice that. And then the last way, which I think was a really good suggestion, Kirsty had kind of suggested this one, is challenging our students to use a different kind of board, like with our polar coordinates, and maybe using the unit circle from week 16 and calling out degrees or radians. We could kind of decide, we'd have to decide on our rules, what we wanted to do, where we wanted to place things, and what we would have to call out. But this is one of those things that I remember Kirsty saying, if you don't remember anything else from this week, kind of memorize some of these things from the unit circle. And I know we all have different ways. Like I saw somebody posted a song that they came up with about the unit circle, but I think this is a good way to kind of practice, looking at the charts that are in week 16, looking at the unit circle, and then still practicing, locating things. So those were kind of the three, I don't know, variations of things I thought we could do. Obviously, Battleship is just fun in general, just playing it the regular way. But there are also, ways that we can kind of tailor depending on the level of our student or familiarity.
So I just want to say thank you, Babs. This was really great. I had not ever thought of any of those other ideas. So you made me think of another one. Maybe Kirsty can look up real quick what page it's on. But we also have the polar axis with the radials coming out. And that's another grid they can learn how to read using a battleship type game. And this was just really dear to my heart because I took the grandbabies camping this weekend, and Lily and I played 2 games of Battleship. And like the apple doesn't fall far from the tree, after the second time, we just kind of laughed and quit because it was so boring. Because like we chose the exact same locations for our battleships twice. So now I can go and say we're going to play it again, and I have some variations, and I don't think we'll play it exactly this. They put them in exactly the same spot. I also think it would have been more fun if the third time when we played, I could have said to her, positive square root of 7 and negative square root of 7. Even though she's just 10, she can say those words, and she can know that the square root of 7 is to the left of the square root of 8 or to the right of the square root of 6. So I think these are all just really good ideas.
Kirsty had another one. I didn't put it up here because my mind was blown at that point, but I think she had one where we could use it for vectors.
So I am putting in the chat, I'm working on putting on all of the game boards that you could potentially use, right? If you wanted to look at a game board and adjust and create one of these. So there's some, I'm just going to hit. So there's a couple of those that may be repeats, but there's some different, like there's a first quadrant game board, there's some 4-quadrant game board. There's a couple where you could use like the angles and the radians. If you go back, I'm just going to go back to where Babs had us on here, right, where we could use complex numbers. If you're just using a coordinate plane, you could, instead of giving the coordinates, you could just say the vector, right? So I'm going to say the vector 5, 7. And if you really wanted to challenge your kids, you could make them give a vector, but then, you could like roll a dice for like a bonus power, right? So they could say my vector's 1, 2, and they roll a dice, and it actually, either doubles the power of their shot, right? And so now they have to multiply their vector. So those were just some thoughts I just had, that you could really take this game and make a lot of different variations. And then maybe it's because I was just talking to my daughter and not my son. So my son would be all about sinking the battleships. I'm not sure about my daughter, although we have as a family played this a lot. And I was thinking, well, what could we do if we have students who are maybe not that excited about sinking battleships? And so I was thinking, you could plant gardens and then pick each other's flowers. That may be too far out there. I was thinking there's a lot of different ways we can change these games up to meet, right, our students and get them interested and still practice the same ideas. Does anybody else have any ideas or stories they'd like to share from their own battleship experiences?
The other thing we used to do is make neighborhood maps on a grid and put things into like one child, Kirsty and I live in the same neighborhood. One of my children could put an X on Kirsty's house, and that's where we have to go find it. You know, we have to go find our house based on, and then did they get it right as far as about how far north and south or east and west is the place that we're going. We also have a few problems similar to that in the curriculum for the little guys where they're going north and south, east and west, up and down, right and left, just to begin practicing reading these grids.
These are also great games to take on the road. So we actually, when my kids would play Battleship, it was usually when we were on the road and we picked up it was just like a pad of paper that had the grids on there. So they'd each take that pad of paper, right? And they do their thing. So exactly like what we have here on the back page. And it was a great game to just take wherever you go because you don't need dice, you don't need cards, there's no pieces to lose, right? So I think this is one of the games that's a really fun game that you can play anywhere. It can be quiet unless you get really excited when you get a hit. Makes me think, I mean, so who wants to date themselves and remember the old ads for this game? And they were always these old guys that were playing, and they would get really like at the end, you sank my battleship. Anyway, maybe we should make an ad with Lee, right? We can have Lee playing with Lily and have Lee be the guy. You sank my battleship.
I wonder if they make, do you know if they, I mean, obviously I could Google or look on Amazon, if they make little grid pads, kind of like Post-it notes, because you could kind of keep those in the car. Do they make them, Jill? I think she does, yeah.
Yep. I
Because I think
keep
that would be really
they're
cool.
posted, they have it sticky even. And yep, and that's grid paper. See, I love grid paper. I love to
Oh,
make notes
yeah.
on grid paper. So yeah, you have that.
Perfect. Okay,
make
so
it.
I'm going to add that to my shopping cart now.
They make it on index cards too, if you don't
Yep,
care about, I'm like, you could just build an index card, but the Post-its are lovely.
yep.
All right. Well,
You
so
know what?
let's
That
go
just made
ahead.
me that made me think about like at a birthday party, we used to play things like pin the tail on the donkey. You can get those big post-its that have the grid on it and play Battleship at a birthday party or a sleepover.
Oh, that's genius. I love that idea.
Or make it pin the tail on the donkey, but you can put your donkey and your tail anywhere, right? And so
In
you
a
put your
quadrant.
donkey on the grid paper, then they have to give you the coordinates instead of blindfolded. They have to give you your
Mm.
coordinates and then they can try to get their tail in the right spot. That would be kind of fun.
Yeah. Well, you can tell we play lots of games, this crowd. Other folks who don't play games will probably think we're a little nutty. I like cupcakes on the grid paper. And I like cupcake papers because they're round. You can use them for your polar axes.
So
Yes, and
Lee,
coffee filters.
I think, Lee, what we need to do is have a Math Map game summit where those that have been, faithful book club attendees, we all get together and we play the games and eat cupcakes.
Love it.
Love it.
I'm totally in. I will come every week if we can do that.
All right. Well, now we're going to go from a game that probably a lot of us had experience with as kids, right? And that's familiarity is what makes it feel easy and approachable and exciting because there's so many memories usually associated with that, to a game that may not feel gamish because it may remind a lot of us of homework assignments from our traditional curricula. And so as we take some of those things, those exercises that are still useful exercises, and how do we make those into a game? How do we make that into something where we can have multiple iterations? I think Lee's done a really great job of thinking through some of those types of activities. And so Jill is going to lead us through missing angles.
So I agree with what Kirsty said, that sometimes this doesn't feel as much like a game, but I think the thing that can make it feel like a game is that we're quizzing each other. And that students, they can either quiz you, the parent, or they can quiz their sibling, or if you have, whatever. We love to get together and do those kinds of things. So maybe they're checking with each other. So if you see here on the directions, that it says that you're going to choose a value between 1 degree and 90 degrees. Now, obviously, when you look at these triangles, you would say that's not 1 degree. And that's where we need to remember that it is also written, figures are not drawn to scale. Because if you try to use a protractor, then you're limited to what your possible answers are. But if you look at this first image here and you see the angle that has an A, a B, and a 30 degrees, right? So you might have an estimate for what you feel like that angle is. You don't have to stick with it. You don't have to be terribly realistic, but you do need to keep it, the directions are here, between 1 degree and 90 degrees for this first one. So in this first one, if you were going to choose a number for angle A, you might say, well, it looks a little bit like 30 degrees. Maybe it's another 30 degrees. And so one student would say to the other, A equals 30 degrees, and then they have to solve for angle B. And so what would that be? What would the measure of angle B be if A is 30 and we're already given a 30?
120.
Very good, right. So then what if
Jan and I
someone,
would race.
yes, you can
You're on.
definitely
Okay.
race. And really, it's great subtraction practice too, especially if someone throws something a little odd out, like what if they said 31? Well, that doesn't sound like it's that far off, but they're going, oh my, it's a 31. It's not just a normal number. So what would the answer to, if someone said 31 be?
119.
Yes, exactly. You could roll dice for it. You could roll 2 dice and say, okay, I have a 2 and a 7, so it's going to be 27 degrees or 72 degrees if you want to keep them from keeping those nice round numbers. You can try different angles. So what we could also say, label all the lines, all the linear 180 lines. So if there's a 30 degrees here in this one, where could we find another angle where's you might not want to do this arc side, but you could certainly do the complementary angle. Am I using the word right? Complementary, not supplementary? Is that right? I did not
If it's a
review this.
linear pair, it's supplementary.
So supplementary. Okay. So the supplementary angle to this 30 degrees, they can find where it would be and what would it be. So what would the supplementary total be?
It'd be 150 because 30 and 150 is 180.
Right. So then you can have them fill them in one at a time. And once you get one thing in, how many other things depend on that one angle? They might not all depend, but if A is 30, does that force any other angle numbers? Or if A is 21, does that force any other angle numbers? The 30 is kind of nice that there's a few numbers that are in there that are, constant for us. And we could look to see, what do they know about the degrees? What do they know about a circle? What do they know about triangles? What do they know about lines? So let's pick another one. Let's say that the angle E, angle F, and the 60 degrees. Okay, and there's still this top image. Somebody might say, well, they look like it's going to be a 60. So your younger children might be practicing their more common triangles. Their 30 and 30 degrees along with their 120. They might be practicing their 60, 60, 60. They might, if there's not I don't see any right triangles here, but they might have, if there was a right triangle, they might be practicing their 45, 45, 90s. So some of those common triangles. But for this one, if your younger child, they might want to keep it simple. So they would say 60, and then we know the third one is 60. But your older child might say, well, how about 65? It's not too tough, but it's a little tougher, right, than a 60. So what would that mean that the last angle needs to be if F happened to be 65?
E is 55.
Right. So then we could also say if E is 55, then D and J must somehow combine to equal what?
180.
Yes, combined with the 55, they have to equal 180. So those two together need to be a total of 125. Is that right? 125. So playing around like that, it's really taking turns, challenging each other to different numbers, trying to stump each other, maybe check each other's math. You could give two kids, if you have two kids who are both in math map, you could have them create their own, but you give them each one, put a page protector on top, and you roll the dice and see who can get through the fastest and how many things they can solve. So they could all be working individually on their own and then compare, and you could even pass and check each other's work. One thing we did in Challenge A previously, other years that the kids liked, we would start drawing a map, whatever we were working on that week, and set a timer for 45 seconds. 45 seconds ended, and we would physically move to the next person's spot and have to continue their map. You could do that with this. You start in 45 seconds, you either stand up and move or you pass this to the next person. They're checking your work and they're seeing what other angles they can fit in. So that's a few ways to get going on this. It's great practice for the fundamental rules that we have learned about lines, triangles, circles, angles, what the totals need to be, those 180s and 360s. So we do have some ideas for ways to add some variety on some other slides.
Something before you go on is I wanted to point out that when you asked about this 60, 60, 60 and said, well, what if you change it to 55? That is perfectly legit. But I'm looking at the symbols that are on there. And for people who don't know, the single tick mark on the 60, F and E says they should be the same. But that doesn't mean you can't tell them they don't have to be anymore. And then the L1 and L2, you see the little arrows to the right of them pointing right. Those mean they're parallel, which of course gives you other restrictions. So you could say, well, what if they weren't parallel? It might be at that point you can't solve as many if you say that. So this is a way to make it a little harder too.
Yes, that is true. Thank you. I overlooked those tick marks, but they do represent things that are the same. And double tick marks let us know that it's the same as another one with the similar tick mark. So yes, thank you for pointing that out. Because those are important things, very important. And we can, probably the first time you're playing, you will want to make sure that you leave those in place, I'm guessing, so that they have practice with those symbols. And then once they're comfortable with that, you can say, now let's pretend those don't exist, and you can do something different. So with our younger students, we can just name parts. And I don't mean just as in that it's not strong work. What I mean is you don't have to take them through this entire exercise if they're not ready for it. You can do the thing that they are ready for. You can ask them to name angles, lines, rays, circles. Words like interior and exterior, words like supplemental and complementary. We can attend to each image and say what is similar or different about the images, noticing those tick marks, comparing angle sizes, even saying, do these look like they're the same? Does one look larger or smaller? Which one on here do you think is the largest or the smallest? Deciding which terms we need to learn or remember using flashcards, those the definitions and the terms we want them to do, and then expressing what we see. They can describe the angles. This one is larger, this one is smaller, this one is obtuse, this one is, well, there's no right triangles on here. But we can, acute, we can use those words. We can trace them. We can build them. We can practice using a protractor and a straight edge and see what they can draw. And then storytelling, how can we describe the idea of 180 in triangles and lines? One of my favorite hands-on things Kirsty and Lee ever showed was how you can take a triangle and you can tear the corners off and tear it into 3 parts and prove that the 180 in a triangle is the same as a 180 in a straight line. So the summarizing and the storytelling of what they know is is pretty great too. Just whatever facts they've learned, whatever they can point to, those are some strong things to do with this page. Then we have some more, slightly more advanced. So students who are ready for the activity as it is can still do some definition. They can start out with what do they see and how do they define these parts. They can compare by inserting different numbers into the angles and see what does that do? How does that change other things? And is there anything we need to, that either is limited or that we need to overlook and change the rules to be able to do? In relationship, what order was most effective in completing this activity? Is it possible to even start with this one angle over here, or do you need to get in a certain order in order to get where it is you're trying to solve? We can challenge each other with different numbers for the angles. We can check each other's work, and then for authority and testimony, what rules did we follow or change, and what laws did we use? So that can even take us to booklet 28 in proofs. If this is not their first time through the math map, they might remember some previous books that they've done and say, oh, I can pull this book and I can add that into this game. If it's their first time through, they're not there yet, and obviously they don't need that. And I think there's one more slide of options. Here's some options and ideas. They can look for angles in the context of oils. Those foundations kids, just remembering, hey, look, we talked about angles in art too. They can practice estimating angles. They could look at one and say, do I think this is probably 40 degrees, probably 30 degrees, probably 10 degrees, looking at what those, drawing them and looking at getting used to those kinds of numbers. Practicing with a protractor and straight edge. Expanding the game idea, they might roll dice or collect cards to find the angles they're missing. So you might try to, if you need something with a 3 in it, you got to roll to get a 3, and then you can quick fill in an angle that has a 3. Adding in more information for students, letting them estimate if the numbers that you chose even seem realistic. If I said that angle A was 80 degrees, does that look realistic on this picture? No, it does not. So why not? Discussing those kinds of things. Using protractors and drawing from scratch and then challenging each other. And so those two go together. Drawing images to challenge each other. So those are a few ways to use this page as is, or use it as a starting point to either help our children reach the goals for this page, or to use the things that we've learned on this page and do new things.
One of the things I really loved about you talking about pulling their resources, because there's so much there that we can talk about: angle measure, parallel lines, circles, linear pairs, right? The supplementary, all those angle pairs, triangles, hexagons, right? There's so much there that we can go and look in those other booklets. And so really, it's a gentle way to remind students, right, to remember, hey, what booklet was that in? What resource? Because we don't necessarily expect everybody to memorize everything that is in the charts, right? I don't think that that's ever been Lee's goal, that anybody would memorize everything that's in the charts. So believe it or not, I have not memorized everything that's in the charts, but I know where everything is. And so there are things that I look up, right? I'll be like, okay, what was the order, right? What was the order? Like permutations and combinations. I'm sometimes like, okay, which one is it? You know where to go and look it up. And so we really want, over the course of several years, for our students to know, hey, I've got this resource. Where is it that I go and look for my answer, right? Where do I go and look? And we all ask our digital devices, right? We all say, hey, so-and-so, tell me this. But there's something really powerful about building that geographic knowledge. Lee is always talking about that geographic knowledge of where in the book, right, is that quote? Where in the book is that phrase that I want to go and look at, or that story I want to go and find again? And so building that geographic knowledge of the charts, and the lesson pages and the other resources so that a student goes, oh, wait, let me go and just look that up. And now I'm going to see it in context and not just this little snippet of information of a digital voice. So I really love the fact that you're saying, hey, remember, you've got all of these resources, and this is a great opportunity, not necessarily when I'm working through the lessons, although I want to do it there too, but in an activity to dive in and say, well, where would you look, right? Where could we go and look to review that, especially over the summer when we're trying to pull those ideas together for our summers. So thank you. Anybody else got some ideas that this activity or some things that Jill shared that maybe made you look at it in a fresh way?
I was thinking with our younger kids, some of this feels like, maybe throwaway because it's too hard for them. There would be nothing wrong with any age student just getting their compass and ruler out and trying to trace right over these shapes.
Or with our little ones, what about like going out and giving them this image and putting them in their sandbox, break their sandbox out, and then have them draw these with their trucks, right?
And then find shortest and longest path. You can talk about the difference between displacement and distance using their trucks on, say, that bottom shape.
Those are very true. And I like the idea of even using a ruler because it is hard to draw with a straight edge when you are young until you've learned how. To hold your pencil next to it, tracing those, and then recreating is tracking, right? When you have to look at one thing and then bring it in front of you, your eyes aren't this close to it anymore.
Something you could do for car school too is to get them to use the language. It's just as you're driving down the road, tell them you want to find somebody point out a tree that's at 90 degrees from the earth. Now someone find a tree that's at 30 degrees from the earth. Somebody find a tree that's at 55. What degrees do you think that tree is leaning at? There's trees and poles and posts everywhere.
One of the things I'm really appreciating as we're working through these games and activities is that we're taking one activity and we're saying, well, wait, we could tailor this. We can change this for younger students, for older students, for students who are at different levels in their calculations. Right? I can take this and pick and choose and make this fit my family. And that's one of the things that we've spent quite a bit of time talking about with the math map is that your traditional curricula tell you to start on page 1 and flip the page, right, until you get to page 200 or 300 or whatever page you get to. Although, Jan, I keep thinking, because I was actually listening to Once Upon a Prime where she was talking about the book and the maximum number of pages being 4,000, right? So all of those fun patterns, we could have built those into the math map. That could have been fun. But maybe we'll save that for another revision because I don't know that Lee could take one more strange mapping. But one of the things that we've really tried to encourage families with the math map is that this is not a start on page 1 and work to page 32, go to the next book, start on page 1, go to page 32. That the math map is really designed to support families in teaching mathematics at home in the way that best meets the objectives of that family and the needs of their students, while still preparing their students to participate in a common conversation in the challenge community, right? So as we think about that, there's a tremendous amount of freedom in the math map. And that can be a little bit scary, right? So if you think about, right, we've all gotten used to wearing a seatbelt, right? So you like strap in and you feel safe because of you're in a seatbelt. And then maybe you go to visit a friend who has a golf cart and there's no seat belts. And there's this kind of crazy feeling of freedom as you think, I could fall out because there's nothing holding me in. And then you have to remember, oh, wait, I'm actually strong enough that I can sit on the seat and not fall out. We have to develop that same confidence when it comes to the math curriculum, right? That we have had a seatbelt on for so long that wasn't just like a seatbelt, a normal seatbelt. It's been like, we've been harnessed into the seat and somebody's locked it, like you're at Disney and you're waiting for them to come along with the key and let you out. And so now we've said, okay, we've unlocked you and we've let you out of this harness. And so there's a little bit of trepidation because what if I do it wrong, right? What if I lean too far forward and I fall out of my seat? And so while we're really trying to encourage everybody, like you can do this, right? You can choose the goals for your math education in your family. You can adapt the curriculum to meet the needs of your students, right? You can pick and choose. You don't have to do 16 lesson pages if it's appropriate for your family to do 8, or maybe it's appropriate for your family to do half of the naturals pages and then half of the complex pages. There's an infinite number of ways that you can use the math map at home, but it's going to take time to develop the confidence to do that and to let go of that harness that we've all had on us for so long. So these activities are a great place to practice with that, right? Because they feel like there's maybe there's not the same high stakes, right? Because it's just an activity, it's just a game. And so this is a great place to say, okay, how do I take this game and explore the freedom I have as a parent, right, to use this with my students, right? And then over time, how could I give my students the freedom to take this game to meet whatever their objectives and their goals are? Because at the end of the day, right, we don't want to raise up children that just do what we're told, right? We want to raise up children who can say, I'd like to learn this and I'm going to go and do that, right? That when they go off to college, they don't need mom to sit there and say, okay, open your book and do the first problem. Now do that, right? We want kids that say, you have given me all of these skills and all of these strategies for learning, and I'm going to take those. And so giving them the opportunity to practice with these games, right, is a way of starting to give them some freedom and to play around with that freedom and how they learn, especially with our older students. But just a thought there to really encourage you to practice engaging with freedom in these games to build up that confidence so then you can take that and apply it to the rest of the math map curriculum.
I really love how you said some of the the freedom and the sort of scary side of not only can I teach my child, but am I okay in setting my own goals? That I think that does feel bigger than can I teach my child math, but am I really qualified to know what they need to learn feels really big.
Well, these book clubs have really helped to give the perspective. Even just going through the games and hearing you all talk, it's creating a new way of seeing things for me. Like it's helping me to visualize that freedom, and it's I can just hardly believe how different I think about math now than I did a couple years ago. It's been revolutionary for me and my family.
That's good to hear. So are we done with our games, Kirsty? Because I have more math to do.
We are done. That gets us to the end of our games, but I will stay and answer if there are some math questions hanging out there or anything anybody else wants to talk about. Just a reminder of all the support we have for you. Next week, we're looking at the games and activities from lessons 11 and 12. On the 21st, we're going to have a tour of the companion, and then we'll be back at games on the 28th. So that brings us to our question slide. And so we can We are happy to answer any questions that you might have.
So I wanted to start with a quick testimonial, and then I have a question too, but I'll try not to talk very long. But you know, I was a Challenge 3 director this year, and for our week 30, I had enough booklets for everybody to look at, and I just had them attend to like the first page of the chart for 3 minutes. I set a timer, nobody was allowed to talk, and they just read through it. And then when I asked them to tell me their, you know, their feedback, the kids, I mean, the ones that haven't been doing the math map, I have a few that have been, but they were like, oh my goodness, this is, if you knew, like if you had all these answers, you'd be set for life. They loved the beauty questions. I mean, I had to cut them off. Well, then we went and had our poetry cafe in an old barn, and we took the math maps along, and we spent time attending to the other pages in the chart as well. It was the best math conversation I think I've ever had. It was so fabulous. The kids all talked about, like the last page has all these things that you can like hobbies and activities and whatever, and how there's math in them. And so each of the kids talked about like maybe their summer job they were getting ready to start, or a hobby they were excited about. And then we all talked about all the different places we could find math in that. And I saw like light bulbs going on. I had one kid say, I have never thought of math as beautiful before. And I I thought people were crazy that said that. And I'm starting to see it. I just wanted to cry. Maybe I did. Anyway, that was super, super fun. Yeah, so that's my testimonial. One student has been doing it all year, and he's what I would call an advanced, like he just gets math and loves it. And he said the only thing that he has to feel bad about, or I forget how he worded it. He's like, I wish so much I could have done this my whole school career. He said, I feel like I've missed out on so much not having the math map as my curriculum. And so that was really high praise too, coming from him. So pretty exciting. Yeah. So can I ask my question quick too, or have I talked too long?
Absolutely.
So it's about this. Let's see, can you guys see? It's this
Yes.
flashcard. Algebraic numbers that are roots of polynomials with integer z coefficients. So I just wonder if you could talk me through what that is a little bit, because the student I'm talking about, Levi, and I have spent a lot of time trying to figure it out, and I don't think we've gotten there. So
let me turn on my pen here. Okay. So first, let's talk about what a polynomial is in its strict definition. So a strict definition of a polynomial is going to be that we have terms, right? So those are things that are added or subtracted. And it could be anywhere from one to several, but we're going to look at where we have more than one. And those terms are going to be made up of variables and coefficients. The variables are only going to have natural powers, right? And so it could be, right, the 0th power of x, the first power of x, the second power of x. Those indices are only going to be naturals. And then are, in this case, right, so a normal polynomial could have any real coefficients. So it could be 2, it could be pi, it could be the square root of 3. But when we're talking about algebraic numbers, we're talking about polynomials that have integer coefficients. So
okay.
4, 3, 2. Right. Now, when I want to find the solution, right, when I talk about the roots or the solution, what I'm saying is what value of x makes my makes, that's really funny that my brain went to an x instead of KES. Makes my polynomial, I'm just going to use P of x to represent my polynomial, equal to 0. Okay. So let me think through Well, yeah, so let's just use the one that we've got here, even though it doesn't necessarily, it's not necessarily going to work out to a nice number. So we have 4x squared plus 3x minus 2. So we could factor this, right? We want to equal 0. The reason why we want to find the factors is because then I can say at least one of my factors has to equal 0. And that's how I'm going to isolate my x's. So as I look at this, I could look at this and say, is there a way that I could factor this by inspection? And that means, do I recognize the relationship between the 4, the 3, and the 2 that would give me nice, even factors? And I'm just taking a quick glance at this, and I don't see a way to do that. So the next way we could do this is by completing the square, or we could skip to our binomial, our quadratic equation. Now, the quadratic equation only works, right, when we have a quadratic function. And so let's look at this. And so this says that x is going to be negative b plus or minus the square root of b squared minus 4ac over 2a, right? And so now I'm going to make sure I can identify this is my a, this is my b, this is my c, right? It's -2, because I could have written this as plus, right? So that's my c. So when I plug those values in, I get -3 plus or minus the square root of 3 squared minus 4 times 4 times -2 divided by 2 times 4. Right. As I look at this, I instantly be happy because I see that I have a negative times a negative, which is a positive number, which means I'm going to actually have real roots of this equation. That's my first question, right? Is it going to be real? So here I end up with -3 plus or minus 9 plus 16 times 2, 32. 9 plus 32 is 41 divided by 8. And I can't simplify that anymore. I could put it into a calculator and get an approximation. But this number, so there's 2 here, right? So x can either be -3 plus the square root of 41 over 8, or x could equal -3 minus the square root of 41 over 8. Both of those numbers are algebraic numbers because they solve 4x squared plus 3x minus 2. So that is an example of an algebraic number. Okay, so it's irrational, right? We see that the square root of 41 is irrational, but it is an algebraic irrational number. Pretty much any irrational number that I can write as the square root of n, right? The square root of 4, yeah, but obviously the square root of 3, the square root of 7, the square root of 62. Those are going to be algebraic numbers, right? My cubes, all of those, right? So I'm just going to, well, let me make this n and p because that matches, right? To the nth root of any power, because I could always write x to the n equals p and x to the n minus p equals 0. So as long as p is an integer here, or a rational number, then I can put it into this kind of equation and it's going to be an algebraic number. In contrast, I, E, I'm going to make up a number that I'm pretty sure is going to be a transcendental number. but 0.101101101110 and so forth. Those numbers there's no way that I could write them as the solution to a polynomial that has integer coefficients, right? There's no way. So the square root of pi, never going to happen. The 15th root of e, right? Once a number's transcendental, it's transcendental forever. So these are my transcendental numbers. And that means that there's no polynomial that can describe those, right,
Okay.
with integer roots.
Which is why on the math map you have algebraic numbers over all of the
Polynomials, right?
yes, but then you have this A with a C, and the complement to the
Yes,
algebraic numbers are the transcendentals.
yes.
But the green bar doesn't go all the way across
Right,
because
because we're talking about, right? So when we're looking at monomials, binomials, and polynomials, and even the expressions, although a little bit different because we're going to be looking at ratios of polynomials. In all of those cases, for the most part, Lee is going to use these kinds of polynomials and binomials, right? She's not going to say the square root of 2x squared. Now something might pop up in there, but in general, right, we're being friendly to our students. And so we're going to use integers as
right.
And just as a note, if you saw a fraction, it's not actually right. So let me just point this out here. And I know I'm like, haven't got this well organized, but let's say that I had 1/2 x squared plus 2/3 x 3 minus 6 equals 0, right? You might say, well, oh, those aren't integers, but notice if I multiply both sides by 6, I end up with x squared plus actually 3x squared plus 4x minus 36 equals 0. And so I end up, right, I can convert that. And so what's roots of one is going to be roots of the other. So even though the definition says that they have to be integers, right, even if they're rational numbers, I can convert that to integers. So as long as my coefficients are not real numbers down here doing weird things, we're going to end up with an algebraic number. And so what we're talking about when we use that A on the domains isn't necessarily to say, hey, right, we're not trying to describe the binomials or the polynomials. We're saying that the numbers that we're going to be working on are going to be the numbers that come from those, right? The solutions that we're looking at are the numbers that come from those in order to build that understanding of, if we understand those numbers, we're really going to start to understand transcendental numbers, which are just weird. They're just weird numbers. And if you think about the real number line, I mean, this to me is when you think about the real number line, we're all pretty comfortable with integers. And then we say, okay, well, get that. Now I feel kind of comfortable with fractions, right? Because let's just look between 0 and 1. And if I go halfway, I get a half. That feels familiar. Well, if I go halfway, I get a fourth. Okay, well, if I go halfway, I get an eighth. I'm pretty familiar with this. And then I say, well, I could always find halfway between any of my two fractions, right? Or a third of the way between any of my two functions or two fractions. So I start to get this sense that there's this infinite number of fractions between 0 and 1. But here's the really cool thing, right? Is that there's an infinite number of irrational numbers between every fraction. Right? How do you even think about that, right? I can't find, right? If you gave me two fractions, I can always find another fraction between them, right? So it's impossible to say, here's the smallest distance between two fractions, right? We can't say that. But yet, between like between every fraction, no matter how small the distance was, there's going to be this infinite number of um, irrational numbers, and really it's an infinite number of transcendental numbers, right? And we can come up with all these weird patterns, right? So you could say, you know, 0.123, 1234, 1235. There you go. There's a weird transcendental number. And so we can make them up, but we don't really understand them, right? Because they're these numbers that exist out there. They don't come from our polynomials. There's more of them than there are the fractions.
Wow.
So
Thank you.
anyway,
That was very thorough and wonderful. Thank you very much. Um,
So Kirsty,
else had a
somebody else
question?
wanted some ideas on how to play Battleship on the unit circle. Babs and I gave two real simple ways, but maybe you had a third or fourth way.
sure. So I was just thinking, and I haven't looked at what you guys put, but when I was thinking about it, if you took your unit circle and no longer treated it as a unit, right? But you could take that circle and you have your angles, right? And we'd have all of these. Now we have all of those angles, and we could actually put, you know, a radius of 1, 2, 3, however many we wanted, right? And then you can still put your ships, right? So I might have a ship that goes through these 4 points. And just because the spacing looks weird, you could still use, right, 4 points to make your ship, if you wanted to, or you could pick different shapes. And so now I would just say, okay, and again, you could either use radians or degrees depending on what you wanted to practice. I could say, okay, pi over 6 radians at a radius of 3, and that would be a miss. And so that's how I was thinking. I would just add in additional radii. So now I can call out my angle and my radius and see if I have a hit or a miss.
So those are drawn in the tops on week 19, lesson 19, as well as on the 4 set for where we do the circles and ellipses, 13. There's polar axes like this that you could play on. Does that help? Whoever asked that question?
So you're just, my brain is so literal. I get so confused on, so you're just, it's not really. So you're just picking, like, say you said the 30 degrees and pi over 6. You're just picking like 3 spots on there?
Yeah, so I would put my ships, right? So I would just I would have, instead of having my grid be like this, I would choose to have a grid that looks like this with my angle measures, right? So I would put my angle measures. So I would have 2. So I'm going to have 1 where I'm going to have, you know, if these are my angle measures, right? Maybe these are the 3 points that I'm using for my submarine or whatever. And so now my opponent would have to call out a radius and an angle. And so let's say they said pi over 4, which would be 45 degrees. So there's my pi over 4. And if they said at a radius of 2, well, now they've got a hit, right? So do my bomb there. That's how I would do it. So that you would have to have 2 of your grids. You would just use a different looking grid. And so you could use your unit circle and draw in other radii, right? So so you could have different radii going out. Those would be those other concentric circles. But you could use it without, if you wanted to just draw that polar grid, you could. But if you wanted to give your students some scaffolding on, you could use that unit circle since it's got those angles that are measured already on there. And that would be a way to scaffold and use that so that they're looking at that. But now I'm just going to add in, it wouldn't be a unit circle anymore if I add in different radii.
And a true radar screen that goes after battleships is actually round like this, not
Yeah, that's what it
rectangular.
reminded me of. I was just thinking about the sonar and the beep, beep as they were tracking things. And so I thought, wow, I think that would really pique kids' interest. And what a great way to learn or memorize those things is in a game like Battleship.
Okay, thank you.
You're
When you
welcome.
were doing this one here, the with the polar, and then I was thinking about the functions on a polar graph. That could be their ship instead of a ship. They could choose a polar function, and as people got hits, they could decide if it was a constant or a quadratic or rational or absolute value. Like you could based on the hits you get try to find the function that that person has chosen too, and you can do that rectangular or polar.
Well, that's fun, Jill.
It's not something I'm probably going to try. It sounds hard.
Can I ask Babs what she posted, that that unit circle you posted, and what you meant with that?
Yeah, I was just thinking kind of more simply that my
Like that.
my pi would be my ship, like my pi, like between 35 and 40, I mean 30 and 45, that would be the section, that's my ship. And then I would just say they would either have to give me 30 and 45 because my ship is between those two, or they could give me the radians that go with those two numbers. So I was just thinking of, like, you know how the like Trivial Pursuit, the pie pieces are like triangle. Like I was just saying that triangle could be my ship or my piece, and they would have to give me the coordinates that touch. So 30 degrees and 45, or whatever the radians are that are associated with those.
Okay, thank you. That's speaking more my language.
All right. Any other questions? All right. Well, thanks everybody for sharing your ideas. Thank you for asking good questions. I think, Jana, I'm really excited you asked that question because I don't think that's something that we've really talked through before, about algebraic numbers. We've sort of used it, but haven't really addressed it because it probably is something that is geared more towards
The
those upper
levels that aren't
challenge
out yet.
students. But
Right.
I'm excited now because what Babs will probably do is go and cut this piece of the video and we can stick it in the companion. And that'll help lots of other people to understand what we're talking about when we talk about that. Yeah,
And when it
Nicole, I think that's a
says,
great
oh,
idea.
sorry.
Oh, so, no, go ahead, Jana. I was
No,
just
I was just gonna say, when that definition says integer z coefficients, you're using either, like, it's almost like in parentheses z, right?
yes.
Yeah. Okay.
Yeah, Lee just likes to, when she puts integers, she likes to stick the z or
The-
naturals. She always likes to put
Mhm.
those symbols
Together.
with the word so that students really pick up and add that to their memoria. But yeah, it
Yes.
would be as though it was in parentheses.
Yeah.
Kirsty,
Or to
Nicole had
use,
a question too about, could you do this same type of polar coordinate on the world map grid? Could you
yeah, I
do,
think that's a great idea.
could you like name the countries too? Like instead of like just the point, I mean, you do want to know the longitude and latitude, but you could like have them say, well, what country is in this section or something like that, since they're supposed to be learning that too.
Yeah, a great idea. Use latitude and longitude and then just being aware. Well, you could even start with, okay, hey, given this latitude and longitude, what continent would you be on? Right? Start with that. Like, so this is really, this is sad, but here's my true confessions moment. Um, I went to high school in Massachusetts. I went to college in Massachusetts. I got my graduate degree in Massachusetts. So I spent a lot of time. I served in the Coast Guard. in Massachusetts. So I spent a lot of time in Massachusetts, and I was really very intimately familiar with my latitude and my longitude in Massachusetts, right? Being in the 40s, around 45 degrees north. And the fact that that's about the same latitude as England, where I was born, right? So, like, for some reason, like 45 degrees north just was kind of internalized as my latitude. And I stopped at some point thinking about the fact that as I has moved, my latitude has changed. It just sort of stayed fixed. So when we went to see Kate a couple of weeks ago down in Florida, and my mom and I went and had dinner at table 26. And it was actually table 26 degrees. And I stupidly asked our waiter, what's the 26 degrees for? He goes, well, that's our latitude. And I was like, oh, yeah. Yeah, that would make sense. Not in Massachusetts anymore. And so, anyway, there's my true confessions moment that I have
That's
been
great.
internally associated with 45 degrees north, and I don't actually live there anymore. So I need to go and look at the map and get a better sense of where I actually exist. So
I love that. Mm.
if you have kids that are really enjoying locations and latitudes, and you haven't looked this up, a new way of addressing the world is called, I'm thinking it's what 3 words, or is it what 4 words? Let me look it up real quick. What 3 words? Yes. So if you Google what 3 words, you will find out that they have taken every 3 meter square of the world, right? So if you think 3 meters is roughly 9 feet, so every 9 square foot section of the world, and they have given it 3 words to assign its, right, that's your location. Because here in our developed world, we have streets and we have numbers and we have PO boxes, right? But in a huge portion of the world, there are no roads. And so you can have latitude and longitude, and that works. But you could also use what 3 words. And so the fun part is that, if your kids were to do this, they might find out that they could each have a different address based on like where their bedrooms were in the house, right? Because your house is going to be bigger than 81 square feet. So you're going to have at least a couple of different addresses for your house. So it's called What 3 Words. And I just think it's another fun way to talk about location. So if you're enjoying that idea of maps and location, that's another thing that you might want to explore with your kids. All right. Well, thanks everybody. I appreciate, as always, having you guys join us as we work through this. I hope that it's being helpful, not just to those that are here, but to those that are watching the recordings. And if you are watching the recording and you have a question and you're not able to join us live, you can always email the Math Map at classicalconversations.com. Send us your question and we will be happy to address it in an upcoming book club. So.
Thank you.
Have a great week, everybody, and I will look forward to seeing you next week.